Hello, this is the first of two videos on holding other factors constant. So this one deals with what exactly it means. The next one will deal with what happens when you do and how that has implications for what you should control for and what you shouldn't. Okay, so this is important for a number of factors. In the past, when I ask students what this means, they basically just say, well, I know at the end of every sentence when I'm describing results, I have to add holding other factors constant. Okay, but it really is important. And one reason why it's important is that it will help you scrutinize models, and that's going to be the main objective of this course. And as I said, it's going to help you determine, well, what should you control for and what should you not control for. Okay, before we get started on that, we have to understand a little terminology. And so for the explanatory variables, or some call it the independent variables, I like to distinguish between two types, the key X or the treatment variables versus control variables. Okay, so a regression is something that tries to model how certain variables move with each other, sometimes while holding other factors constant. And there are four main objectives of regression analysis. This is in section 2.2 of the book. The one we're going to deal with here is the primary one, which is estimating causal effects. Okay, and in such a model with that objective, then the key X or the treatment variable would be what I consider the catalyzing variable, or the variable that you want to know how that variable affects some outcome. The control variables, in contrast, are just going to be those variables that you're including in the model to help you get the best estimate for how that key X variable affects the outcome. Okay, so it doesn't matter that you're getting an unbiased estimate of for each of the control variables, but you do want an unbiased estimate for the coefficient on the key X variable. We're going to deal with two issues to demonstrate holding other factors constant. The first one is a conceptual one. The second one will actually use data. Okay, so this first issue, one that's very important to me, does adding cinnamon to your chocolate chip cookies make them better? Okay, so take a moment, think about what would be the key X variable and what would be possible control variables here. And I'll give you a little hint. The dependent variable would be the taste of the cookie, which would indicate, hey, does it taste better or not? Okay, so hopefully you figured out that the key X variable is equal to, or is the cinnamon. Okay, that's the catalyzing variable. That's the variable you want to know. What is the causal effect of the cinnamon on the taste of the cookie? Okay, so for control variables, well, there are many possibilities. I would think that the key ones would be the amount of butter, the amount of chocolate, and the amount of sugar. Okay? All right, now let's think about which of these two is the better test and why. Okay, so test A, you're making two separate batches from scratch. When one of those batches you use cinnamon, and the other one you don't use cinnamon. In test B, you make one batch, you stir really, really well. You then divide the batch into two. You add cinnamon to one of them. Okay, take a moment again to think about which is the better test. Okay, so I would choose test B. And the reason for this is that the only thing we want to be different between the two batches is the cinnamon. We don't want there to be anything else that can affect the outcome and to be different between the two batches. That is, we want the two batches to have the same amount of butter, chocolate, and sugar. Okay, so if I were to ask you to describe this using that phrase, holding other factors constant, again, take a moment if you wish. Okay, so what I would say is I want to know how cinnamon affects the taste of the cookie, holding constant butter, sugar, and chocolate. Okay, the second issue deals with how does class grade point average affect the evaluation of teachers or instructors by students. And this is important because a lot of schools use these evaluations to judge the effectiveness of the instructors. They may use that then for promotion and tenure. Okay, but the problem could be that there are biases in these evaluations. Some have found gender biases, and there has been some evidence that grades actually affect evaluations as well. In fact, that's something that I've been working on. Okay, so I created some notional data, and let's say that there are 3 professors we're evaluating. We'll call them A, B, and C. No relation to anyone we might know. And let's say that each of these 3 professors just teaches one course, just to make things as simple as possible. Okay, so I created some notional data, and in that data I created 50 observations for each professor. That's 50 different classes. Okay, and for each of those classes, so there's 150 total observations, and for each of those classes I have an average evaluation, we'll call it E, and that's on a 1 to 5 scale. And the key X, that's the dependent variable, and the key X variable is the grade point average, GPA. And that would be the average grade in the class on a 0 to 4 scale. In reality, it's going to be in the 3 to 4 range, from basically a B to an A. Okay, so our simple regression model would simply have E. E would be our dependent variable. We're regressing that on GPA. Okay, just as in every other possible causal effect out there in society, the effects of GPA and evaluations are different for the 3 professors. Okay, so here are the effects that I imposed on this notional data, but we have to act like we don't know what these are. Okay, so for Professor A, I gave an effect of 0.0. For Professor B, his or her beta 1 is 1.0, and C has a beta of 2.0. So basically says for Professor A, grades do not affect evaluations. For Professor B and C, the grades do affect the evaluations, more so for Professor C. So again, the mortals among us do not know what these actual effects are. Okay, so let me ask you, what is the true average treatment effect? And let me give you a little hint. There are 50 observations for each professor. Okay, so take a moment to think about that. Okay, so the true average treatment effect, because there are 50 observations for each professor, it's just going to be the average of these 3 effects. And so it's going to be 0 plus 1 plus 2 divided by 3. And that's going to be 1.0. That's going to be the true average treatment effect. Okay, but we're not going to get that for a couple reasons. And one of those reasons is that I added randomness to each of these average evaluations, and so that's going to prevent us from getting these exact effects. This graph shows the 150 observations, the 50 observations for each professor, and it demonstrates the randomness as well. So for Professor A, I kept all the average GPAs in the 3.0 to 3.2 range. And for Professor B, I kept all those evaluations in the 3.4 to 3.6 range, and then Professor C gives much higher grades, 3.8 and up. Okay, so again, this has no bearing on any reality. The grades I give aren't quite that low, and certainly my evaluations aren't that high either. Okay, now if I didn't add any randomness to the evaluation, then all the data points for a given professor would lie in a straight line, just a straight line of slope of 0.0 for Professor A. That's his or her beta. Slope of 1.0 for Professor B, his or her beta, and 2.0 for Professor C. If I actually did this new randomization an infinite number of times, then the average of the betas for each of the professors would be exactly 0.0, 1.0, and 2.0. So that's how this randomness works. Okay, so let's start with a simple regression model where we do not control for the professor. Okay, so we find the line that best fits the data, and that's going to give us this equation up here, where E hat equals 7.88 minus 1.02 times GPA. Okay, so first you might be confused because we're getting an intercept here of something like 4.85 or so. Okay, that's the predicted value when you have a GPA of 3.0. If we actually move the graph way to the left and went to a GPA of 0, then the predicted value would be 7.88. Okay, now what hopefully you should find disturbing is that we have a coefficient estimate on GPA of negative 1.02. And we know that's wrong because we see that there's an upward slope for at least 2 of these professors. And so it really can't be a negative effect. Again, we don't know we don't know that the average treatment effect is 1.0, but we can be pretty sure it's not equal to 1.02. So let me tell you what the problem is. In the chocolate chip cookie example, we wanted it so that when we went from one observation to the next, the only thing that was changing that could affect the outcome was the cinnamon. None of the other things, the butter, sugar, and chocolate, weren't changing. In this case, as we go from one observation to the next, we want the only thing that changes to be the GPA. Okay, so let's start here on the far left. As we go from left to right to the different observations, the only thing that is changing is the GPA because we're sticking with this professor. But then we get to this point, and then when we go right to the next observation, well, now something big has changed, the professor. Okay, and with the professor might come different evaluations. Okay, again, we move left to right. Okay, and now the professor is staying the same. But then at this point, as we go to the next observation to the right, well, now again, we have a different professor, and that could affect the evaluations. Okay, so basically, we're not holding constant the professor, and that negative 1.02 might be picking up the professor effects on the evaluations. And that's why we need to control for the professor. Okay, so as we control for the professor, then our new equation is going to be this. We're regressing the evaluation on GPA, and then we have 3 different professors, so we have to add 2 professor dummy variables in there. Leave one out, and it turns out it doesn't matter which one you leave out, and we don't care what these beta 2 and beta 3s are. At least I don't care what they are. What's important is that we want the best estimate for beta 1. Okay, and if you do use A and C or A and B instead as the 2 professors, you're going to get the same beta 1, and you'll see why in a moment. Okay, so now I'll show what actually happens behind the scenes, behind the curtains, when we estimate this. Now, in the very first paragraph of Chapter 6, I actually give you a better description of what's going on inside your computer when you try to run a regression model. But here I'm giving you some snapshot version here. Okay, so what the computer is doing is that when you control for the professors, then in a categorization like this, then it's going to estimate the slope for each of the professors, okay, or a different regression equation for each of the professors. Okay, now the intercepts aren't so important. What's important are those beta 1s, beta 1a, beta 1b, and beta 1c. Okay, and again, if we did this an infinite number of times, then the average coefficient here would be 0, 1.0, and 2.0. So for Professor A, we got something somewhat close to 0.18. And again, we do not know that these are the actual effects. I mean, I guess I know because I created it, but we have to at least pretend like we don't know. Okay, so got something close for Professor A, a little even closer to the 1.0 for Professor C, and Professor C is very close. And it's just by chance that they actually all 3 happen to be greater than the true estimate. If I were to do it again at new randomization, it would be a little different. Okay, now what's important is that these 3 estimates, based on within professor comparisons are what's going to go into the estimate for beta 1. And how do we know that we've held constant professor? Well, now we're only doing within professor comparisons. Okay, so a given observation for Professor A is only being compared to the other 49 observations for Professor A. They're not being compared to any observation for Professor C or for Professor B. Okay, and the same thing for Professor B. All Professor B's observations are compared to the others for Professor B and not to anyone else. And that's how we know we're holding other factors constant. And so what happens when we control for professor? Then as the GPA changes, professor no longer changes. It can't because it's held constant. And all comparisons are within the professors. And so the regression that we get is now going to be this. Again, I don't care about these, but what's important is that we have an estimate of 1.14 on the GPA. Okay, so that's much closer to the true average treatment effect, which again, we don't know. We don't know it's 1.0, but this 1.14 is closer to that 1.0 than the negative 1.02 in the simple regression model. Okay, where does this 1.14 come from? Well, it's roughly the average of our three coefficients here. Okay, now the average actually comes out to 1.12. It's going to be slightly more weighted to Professor C. So it's actually a weighted average of these three. The weight will be based on the number of observations, which is the same for the three professors, and the variance in the GPA. And because of that big gap there, the variance is actually going to be slightly higher for Professor C, and that's why the 2.06 is getting a little higher weight, and this will be a little above the real average of 1.12 for the three coefficients. Okay, so again, what's important? The coefficient is now a weighted average of three coefficients from only comparing a given professor's observations, not comparing observations from one professor to the other professor. Thus, the professor is now being held constant. Let me make a distinction. So in the actual data, as GPA changes, then so does the professor. But in the model we created to try to estimate the causal effect of GPA on the average evaluation, well then, as GPA changes, the professor does not change because we're only looking within professors. Okay, last thing. If we were using actual data rather than the notional data that I created, then something I said earlier wouldn't hold. So I said that, okay, when we're looking within professor, the only thing that's changing that could affect the outcome is GPA. Okay, so in my notional model, that holds. In actual data, well, things actually could change. So one class for a given professor might be different from other classes. There could be a difference in the number of students. There could be a difference in just how well the professor ended up connecting with the students for a given class. And so because these other things do change, then we probably want to control for some of them. Okay, so let's add the number of students to the model. Okay, so here's our original model. And here's the model where we add at the end beta 4 times S. S is the number of students. Unlike the variables for Professor B and Professor C, which are qualitative variables to represent a categorization, the variable for S is considered a quantitative or an interval variable. And it's not going to be as clean an interpretation. So when we control for it, then we're basically taking out the linear effect or the linear relationship between the number of students and evaluation. But there's undoubtedly going to be some nonlinearities. Okay, so as we control for the professor and the categorization of which professor a given data point is, we know that as GPA changes, then the professor does not change. But adding S into the model, we can't be certain that as GPA changes, the number of students doesn't change. So it works towards making it so that as GPA changes, the number of students does not change. But we can't cleanly do that with a quantitative variable. And so the conclusion from this is that adding a quantitative variable to a model is not as clean for making sure it does not move with the key x variable. The next video will show you a little more about what happens when you control for a variable, and that will help you determine what you should and what you should not control for.